All right, so the recording has started. Please let me know if you've, for like at any instance during the lecture that my voice breaks or if like the video stops or something like that. My internet is sadly still very bad and it might stay that way for the next week, but hopefully after that it should be fixed once I get back to Paris. So let's get started. Last week we started speaking about object detection in general. And we spoke about things like what is object detection? Is it something that is classification? Is it a regression? We spoke about the applications of object detection, things like vehicle counting, things like facial recognition or facial detection mainly, parking lot monitoring and application to smart cities. Yeah, vehicle counting was the application to smart cities. And then we started speaking about how can we approach this issue of object detection, right? So the first way was to just apply a image classifier multiple times on that same image. So we first start applying it on different regions, let's say, for example, at the top left, and then just move through the image with a certain stride. So for example, maybe stride of 1, stride of 2, stride of, I don't know, stride of the size of the window, as you wish. And then we said that this one, especially if we use a small stride, so a stride of 1, for example, if it's a 3D, if it's an HD image, then it's going to have like, I don't know, 1,000 by 1,000. And we will be applying it 1,000 by 1,000 times, which is like a lot of applications of the CNN, which is a lot. So we decided that maybe for speed improvement, we use this idea of pyramids, right? So increasing or putting different sizes of that image and applying the classifier on them. And whatever the small classifier finds a potential location where objects are, we try to zoom the image back in and make it a bit bigger and focus only on these regions where the smaller classifier was doubting the existence of an object. We said that this idea is pretty nice, but much better idea would be to use a search algorithm, something that is able to find patterns in the image instead of just randomly searching around the image for like different locations. We said that this might not fit all types of objects, mainly because it's restricted to the size of the objects, although we are, applying it 1,000 by 1,000 times, but still we're not taking all the aspect ratios. So some objects might be rectangular, some objects might be horizontal and long, some items might be, vertically long. Some others might be, circles, triangles. So there are different types or different shapes of objects, and forcing the size of this red window on all of them is not going to work. So, well, the idea of selective search came up, especially since we already saw something similar to it during the interpretability lecture, which was superpixeling. For selective search, what it does very simply is it looks at the pixel values, and if there are pixels which are close together and are similar in terms of like brightness, in terms of pixel color and pixel values, texture, and all of these other features, we will just group them together into the same, let's call it potential object, right? And then if we find, for example, these red pixels are close to another potential cluster of white pixels, we just group these also together and propose a new object location. So this selective search algorithm, as you can imagine, is a greedy algorithm that tries to combine basically these different pixel values or different pixel regions together into a object proposal. We said that in order to actually evaluate whether these object proposals are nice or not, we have a very interesting feature that is called intersection over union. So intersection over union is a metric that is used to evaluate the similarity between two different rectangles, right? Or two different regions. So you will see it also when we later speak about things like segmentation. We will be still speaking about intersection over union, although the calculation will be a little bit more slower, but it's again the same concept, right? So what we do is we take two different regions for two different shapes. In our case, for object detection, we're taking two rectangles, and we take the intersection divided by the union. As the union is always bigger or equal to the intersection, so the maximum value that this feature can get is 1. And also, as the intersection can never be a negative value, so it's always either 0 or something higher or something positive, that means that this intersection over union is a feature or is a metric that is always restricted between 0 and 1. Things that are between 0 and 1 are always very nice for us in the field of computer science, and that's because we can do a lot of processing on them, and we can interpret them in a much easier way, right? So for example, if somebody was just using something only like the intersection, when we say an intersection of 0.1 or an intersection of, I don't know, 1,000, what does that mean, right? Maybe 0.1 was a good intersection, but the 1,000 intersection was not very good. So we must at least, divide it or normalize them by something that gives us this perspective of how good it actually is compared to other things, right? So it always goes between 0 and 1 or 0 and 100%, and that's much more interpretable, at least by human beings. And then we said that there's a major issue with most or all object detection models. So even till now, we've seen it even in things like YOLO v4 and YOLO v8, even till now, all these object detection models suffer from the same thing, which is re-prediction of the same object. So we predict the same object multiple times. And this is mainly due to the fact that we use, these search algorithms, and then we apply the second step, which is the, what is it called? The actual classification, or even when we later see the YOLO version, is that we will see that the different applications are or the different classifications are distinct from each other. So we're not going to use the information if we find that pixel 9 and 8, we found an object there. If we go to pixel 9 and 9, and we also find that same object, we're going to detect it twice. We're going to say that we have found a new object, although it's not a new object, it's the same one. But just because we applied the classifier multiple times on a very close region, it will have this potential, how do we say, prediction of the same object multiple times. And the algorithm that we used to fix this thing is called non-maximum suppression. And thankfully, we got 3 people who actually predicted what this algorithm actually is, thanks to their amazing skills in algorithms and data structure. And this algorithm, we said, is pretty simple. So it starts with all the predictions from the model, and then takes the highest prediction and puts it in the final results that called final proposal list. And then just keeps on calculating the intersection over union with every other prediction out there. If the intersection over union is above a certain threshold, we remove this prediction and consider it as a duplication of the same object. If it's not above that certain threshold, then we leave it and we try to find the next ones. Once that is done, we go and find the new highest highest confidence score object proposal, and we put it in the final list and compare again the same with all the other remaining proposals, until we end up with the initial list or the proposal list from B, 0 proposals, and the list D as the final list of proposals. And then we spoke only about RCNN in general and said that RCNN is the algorithm that we have been describing from the start of the lecture. It only simply takes the input image, extracts the regions of proposals, which are basically the output of selective search algorithm, which is, as we said, a greedy algorithm that is based on the hypothesis that objects should have pixels of similar colors or similar intensities. And then what we do is simply take whatever the selective search has proposed, resize it into the same shape. And remember this resize or wrapped region calculation. It's just a simple resizement, but it is a very, very important important operation, especially for the future models, since we will see a little bit of improvements. We will remember this extremely important feature, or extremely important calculation, right? So we resize them into the wrapped region that we would like. So it's just the size of image that we only work with. That's because we are using, as we said, a classifier with a fixed, fixed CNN layers, and everything is fixed in it. So everything should have the same size. And then the last one is definitely the classification of whether this is an airplane or not, if this is a person or not, or if this is a monitor or not. So this is what we have discussed during that first lecture of this course. So this is pretty easy. We said that this is selective search. We said that this the idea of RCNN, the initial model of the RCNN family, is pretty problematic, mainly because during the training time, it will do 2000 classifications per a single image. So 2000 classification, the number 2000 is mainly because the selective search on average would propose around 2000 images or 2000 region proposals for that same image. And then we have during the inference time, which is also sadly very long because we will apply the CNN for 2000 times, and that usually takes around 47 seconds, even on a good GPU. So the inference time is pretty slow, the training time is pretty slow, and the only issue is it takes 2000 applications or 2000 passes through the CNN. Another issue, selective search is a bad algorithm because it is a greedy algorithm. So those of you who have done, of course, all of you have done, of course, on algorithms and data structures, and you have seen what greedy algorithms are, and you probably know that any algorithm that is based on a greedy approach that is using a heuristic is never going to be an optimal algorithm. So it's not even trying to be an optimal algorithm, mainly because for some situations, it might not work, right? So for example, it might not work for things like medical images. It might not work for what are they called? Museum images, artistic images, things that are different from this hypothesis of pixel intensities are what makes the objects, right? So for example, maybe there are some objects which are not similar in pixel values, but still they are pretty, they are part of the same object. So maybe a zebra, for example, it has like pixels which are black, and then pixels which are white, and then again pixels which are black, and then again pixels which are white. So it might take multiple merges to actually find or to propose the whole zebra as an object. So maybe that could be a limitation. I'm not sure if that's like that's the perfect example for the limitations of for selective search, but that could be a place where selective search might not work. So for example, if your object itself has this issue or this heuristic violated, meaning that the pixel values of your object are not grouped together, or they don't have the same color values, but for example, it is grouped together by something like what is it called? By the texture, right? So for example, if you are in a in the snow, and there is a what is that called? The white bear. Yeah, there's a white bear in the snow. So you might not be able. Oh, rainbow. Yeah. Yes. So rainbow has lots of colors, and reaching that region where it is all classified together might take some time. Again, for some cases where your object has the same pixel intensities as the background, this algorithm will fail drastically. So for example, snow and those white bears, they all have the same color. This algorithm is just not going to work well for them. So this is why we're saying that the limitations of selective search are very bad. We're not going to worry right now about selective search, mainly because problem number 1 and problem number 2 are a much worse problem than the actual selective search, being slow or being something like that. So our main issue right now is with the concept of passing 2000 images for classification. And this is what we'll be solving during the fast RCNN architecture. So for the fast RCNN architecture, he has proposed a very, very simple idea, an extremely basic idea, which is do not pass the what is it called? do not pass 2000 images through. So like this, we have 2000 region proposals. Each one of these region proposals will go through the CNN. So what they thought is, do not do that. Take these 2000 region proposals and only pass them once through the CNN. So there is only one single pass through the CNN. One person would be saying, well, how does that happen, right? So how is that even possible? Hey, Rainbow. So how is that possible to pass 2000 images through the CNN, but only once? The idea or the trick is extremely basic. So instead of doing 2000 these 2000 region proposals, instead of doing that first, let's put one image through the CNN. That's step number one. So one image goes through the CNN, step one. And then step two, find these 2000 or apply the greedy search algorithm for these 2000 images. And then you will have the classification. Sorry. So you see this, the order, just the order that has changed. And this leads to a change a bit in the architecture, of course, but that's it. That's the only thing that has changed. Classification. Classify. So here, as we said, we take the whole image, not just the region proposals, the whole image, pass them through the CNN. That gives us a convolutional feature map. This is pretty easy. This is one single pass of that whole image, not of a single region of the image, not of multiple single regions of the image, but of the whole image together at once, goes through the CNN only once. That solves already the majority of our issues. And now once we did this step number one, we go to step number two, selective search. Now the issue is we cannot apply selective search on a convolutional feature map because selective search requires actual pixel values. So we can't, for now, we cannot do the search on the convolutional feature map. We must do it here. So here, step number two, apply selective search and get 2000 region proposals. Now, what do we need? We need a convolutional feature map, a small, let's say a small convolutional feature map that is related to each one of these 2000 region proposals. So we need 2000 different convolutional feature maps. Can somebody tell how can we get 2000 feature maps from what we have already in here? Nothing extra, only what we have already calculated. We have a convolutional feature map, a big convolutional feature map. We need small, 2000 small convolutional feature maps. Can anybody tell me how? Vladislav, I'm not sure if you are speaking, but I can't hear you. Can somebody speak just to confirm that I can hear you guys?
Yeah, can I guess?
Oh, yeah, this is the issue. I cannot hear you. Yes. Let me see. Can you speak now?
Can I guess?
Perfect. Go ahead. Yeah, now I can hear you.
There is such thing that is called network in networks, and it allows to increase amount of feature maps on the yeah, of the output
Seems
of
like a
the
great idea.
convolutional network.
But you are thinking too complicated. You are thinking in a very complex way. Let me give you a clue. Kareem is right. So Kareem is at a very good place. Continue. Maybe try to base on that idea and find a solution. Kareem Galimov, can you hear us? Yes, go ahead. Try to, from that sub-regions idea, try to just give us the actual algorithm, step by step. You are correct. It's based on these sub-regions, but how?
So probably at the end of CNN, we have A as you said, activation maps, each B by B. And what we may do, we may split this B by B maps into K by K, where K is smaller, and choice of K is probably some hyperparameter.
Okay, let me, the K for us right now is 1,000, just means 1,000. Let me just ask you a small question, huh? Don't leave. Small question.
Mhm.
For this region in the image, this green region, can you see it?
Yes.
Where do you think its actual convolutional feature map should be located in this gigantic convolutional feature map? Where it should be?
Also somewhere in the corner.
Also
Yeah.
somewhere in the corner, right? So if selective search proposes this head of the horse as a potential object, where do you think the convolutional feature map of this head of the horse should be located in the gigantic convolutional feature map that we have here?
In the center, bottom center.
Also in the same region, right? So what ends up happening is we can easily do a calculation that goes immediately from here, from a region on the image to a region on the convolutional feature map. Very simple calculation, right? And that's what ends up giving us the 2,000, from 2,000 region proposals on the image to a 2,000 convolutional feature maps with 0 calculations, or with almost no calculation, no significant calculation, right? So previously, how were we calculating these 2,000 convolutional feature maps? By passing 2,000 images through the CNN. Now only the whole image goes once through the CNN. Goes through the CNN only once. CNN. Only one time. And then that gives us a convolutional feature map that is gigantic for the whole image, right? And from this convolutional feature map, with a small calculation, convert the location of these 2,000 regions on the initial image to a 2,000 location on the actual convolutional feature map. And then, as you can imagine, once you have a couple of feature maps, you just pass them through the what are they called? Through the fully connected neural network, and that's going to do the actual classification. So the actual classification will be done with 2,000, of course, applications over the fully connected neural network, or the multi-layer perceptron. But that's not a bad thing, because fully connected what is it called? Yeah, fully connected neural networks are very quick to do the processing, or very quick to do their calculations. So it basically leads to a much faster calculation, or instant almost calculation over the neural network. So here what ends up happening is the following. We have, let's say, this big object that was proposed to us by the selective search. So its size is this, right? So it has a big convolutional feature map. Let's imagine that we proposed, or that we had another proposal by, of course, selective search on here, but it's much smaller. So its convolutional feature map should also be much smaller. Logical. These two different convolutional feature maps will go through the same fully connected layer. Is that correct? Yes, it is correct. Can somebody now tell me, first of all, how did we solve this issue before in the RCNN, having this issue of multiple images going through the CNN, the same CNN, or they have different sizes? How did we make them all the same size? A very simple word, just one word. Resize. Oh, thank you, Paulina. So we just resized the image. There is something that is called resizing the image. It's not a big concept, very simple concept. But now we are speaking about a convolutional feature map. We need the concept of resize, but for a convolutional feature map. So convolutional feature maps are, again, just images, right? They're just matrices, but instead of having, RGB channels, they now have multiple channels. So the channels that they have are channels like, does a nose exist in here? Does an eye exist in this place? So just different activations based on whatever whatever pattern they're trying to recognize. So these convolutional feature maps are just basically images with not RGB as channels, but more complicated, abstract information that is being calculated at the channel level. How can we apply the resize? And here I'm going to ask you to remember something that we did during the first week or the first lecture of this course when we spoke about CNNs. What are the different layers that you can find in a CNN? Go ahead. Throw words. You have a convolutional layer. Anybody knows another type of layers? Dropout. Well, dropout is technically a calculation, but in the implementation of, yes, all of these things are layers implemented, fully connected layers. This is at the end. Yes, fully connected layers, part of the CNN also at the end. We also have another thing that is always pooling. Yes, perfect. So pooling. What is pooling? Do we have a specific type of pooling? Average pooling or something like that? Maybe something specific. Max pooling. Even better. Yes. Can somebody tell me how does max pooling work? Right. So it takes, for example, a region of 3 by 3, and what it summarizes it to a single value. What is that value? The maximum. Wow, you guys are following very well. Now let me take this up and clean up a little bit. Let's stop. New share whiteboard. Can I do this? I don't know. Can you now see the whiteboard instead of the slides?
Yes.
Perfection. So let me draw something. I'm not very good at drawing, but let's see. I'm gonna need your help here, guys, huh? Opa. 1, 2, 3. 1, 2, 3. I'm gonna put some numbers here. 2, 3, 4, -1, 5, 9, 9. This is 5, huh? And 1 and 0. This is a certain size. I would like to put this image, 3 by 3 image, into a 2 by 2 image. How can we do it? Do not think of max pooling. I want you to think of a way to split this image into 4 by 4. So can we split in the half? Can we split this pixel like on the half? We cannot. So we must choose either from this place or from this place. Any of these choices works well. You can choose, for example, to put the one that is in the start to be the biggest. So like this. And then we also split this into 2 by 2, like this. Now that we did this split, can somebody tell me what should be the value of this pixel?
5.
First pixel. 5. The pixel next to it.
9.
9. Pixel next to it, or the one in the bottom.
9 as well.
And the last one.
As well 9.
Oh. Take it again.
Why 0?
You see this split? See how we split them?
I got it.
Oh yeah, exactly. Let me split it again here. Hopla. Hopla. Like this. So basically this first top region, or this first, the first pixel in here, should be the maximum of this place, right?
Can I ask?
The 9 should be the maximum of these two. This one is the maximum of these two. And the final one is the maximum of this one. Make sense?
Yeah, can I ask?
Yes, of course, go ahead.
So can we do the following? So we have this 3x3 matrix, and
Yes.
we are considering the maximum of the first 2x2 sub matrix. But
Yes.
then can we have a step 1 in horizontal way, in the right way, and consider submatrix 3, 4, 5, 9?
Absolutely. There's nothing stopping you from doing anything you want, right? This is just absolutely, if however you want to define it, you can define it. Yes. So just the max pooling that
okay.
we are like looking at just takes the first two, like the first pixel to be the biggest, and then the other ones as the smallest. But it's up to you. You can define, these things as you wish. There's no right or wrong answer. There's no better or worse.
Okay, thank you.
Okay. So this is it. The actual, like, what is it called? The actual algorithm of this idea of resizing is called ROI pooling. So we've seen something called max pooling, right? Now we are seeing something called ROI pooling. ROI stands for region of interest. Region of interest pooling. So region of interest pooling is a pretty similar technique to max pooling, but instead of having, a window, fixed size window that is being slided through the image, now we are taking that image, we manually split it into however much regions we want. So if we want 2x2, we take our matrix, split it into a 2x2, and then we take the maximum of those regions. If we want a 5x5, we take whatever matrix we have, split it into a 5x5, and that gives us our output matrix, right? So this is ROI pooling. ROI pooling is almost similar to the concept of resizing, right? You've seen resizing. So it's very similar to the concept of resizing, but it's being applied, instead of being applied to the actual image, it is being applied to a convolutional feature map. And that's it. That's literally everything that you need to know about fast RCNN. You now know the architecture of fast RCNN from the start to the end. So the actual genius idea that fast RCNN came up with is, instead of doing, the selective search, getting 2000 images, passing them through the CNN, how about we actually start by passing the initial image through the CNN only once, and then apply selective search, and only do a mapping from the region of interest that is inside the original image to a convolutional feature map associated with that region of interest. That means this resizing operation has now shifted from the actual image space to the convolutional feature map space, and we renamed, or we now call this resize operation as a ROI pooling instead of calling it as a resize. So, but the actual calculations is exactly the same. And that leads us to seeing how that's being done. So for example, if, if selective search has proposed this, this object here with location, 340 by 450, this is the X and Y. So these are the X, Y coordinates. And the actual, width and height was 320 by 128. So this is the width and height. And we have this information that the input image is 16 times bigger than the actual convolutional feature map. Simply, what do? Divide everything by 16. This is the only thing that you need to do to go from applying selective search on the input image to finding the actual location of that ROI proposal in the convolutional feature map. So it's only a division by 16. Very simple operation compared to passing it through a whole CNN with thousands, if not millions, of multiplications and additions and stuff like that. Only a single operation. And that gives us the whole architecture of fast RCNN. So this is it for fast RCNN. As you can see, it's a very simple architecture, as we said, but it leads to a much better improvement in both training time. You see training time in hours goes from 84 hours to only 8 hours. So this drop is like, I don't know how much, 10 times faster. So it's a 10 times faster operation, fast RCNN. Amazing. And then for the test time, for the inference, right? It goes from 49 seconds all the way down to 2.3 seconds, which is amazing, right? So this is a drop in, or like an increase in speed that is more than 25 times. Yeah, 25 times faster, right? So it's a very big increase in speed in inference time, 25 times faster. Amazing. Only one problem remains. What is the problem that remains? Remember our CNN problems? We had 3. Solved 2. Now 1 remains. What is it? Что это? Проблема. What if the size is less than what we need? Then we just make it bigger. That's an amazing question, Sophia. Yeah. If it's smaller than what we need, we make it bigger, right? So we duplicate those pixels. So what is the problem that remains here? Remember the 3 problems that we spoke about? Training time, inference time, and the last one. What is the last one? Selective search is not dataset specific. So this issue we still have not solved yet. We've solved the training time issue. We've solved its inference time issue a little bit, but we still are using selective search. So selective search is not dataset specific, and that leads to bad results in general. Now there is another problem. Previously, the 2000 passes through the CNN was taking the biggest amount of time, right? That was the most, time-consuming part of our architecture. Now, the biggest time-consuming part is the actual selective search algorithm. Let's look at it. So this is RCNN with selective search and without selective search. And as we can see, with selective search, it's 49 seconds. Without selective search, so if we don't calculate selective search, we just take away that calculation, it becomes 47. So clearly, the issue of speed is not because of selective search. But if we go back to, or we go down to fast RCNN, and we compare now, including selective search, it is 2.3 seconds. Without selective search, it is only 0.30 seconds. What is the biggest time-consuming operation of fast RCNN then, in your perspective? Anybody? Selective search. Thank you so much, Nadeem. So yeah, selective search is basically the hardest or the slowest operation that is being done in fast RCNN. So somebody would guess faster RCNN, it's only included, it's only, increase in the architecture is replacing selective search. Nice. Does anybody have a question about fast RCNN for now? Right, what is fast RCNN? So going from RCNN to fast RCNN, does anybody have a question about that? So хорошо? All good? If it is all good, do you want to take like a quick 5 minutes break and then come back and finish the rest? Or do you want to take to finish basically the whole thing and then take the break at the end? Can you briefly repeat the algorithm? Absolutely, yes. Fast RCNN, here he goes. Step 1, CNN. The whole image goes through the CNN. Let me type it. One image through CNN only once. 2, apply selective search on image. 3, map ROI, regions of interests, proposals from image to convolutional feature map. 4, ROI pooling to make all convolutional feature maps same size. 5, classify using fully connected neural network, or let's call it multi-layer perceptron. So these are the steps. Very easy steps, very basic steps, very simple, very logical. Anybody else has a question about the what is it called? Fast RCNN architecture?
No.
Хорошо. Let's go to faster RCNN then. So faster RCNN, even in the architecture itself, you will see something called fast RCNN network. Here it is. So this part is exactly the same as what you have seen already. It's all the same. The only thing that changed is this part. This got included. So this was a bonus. This is a new thing in faster RCNN. There's no longer a concept selective search. There's a new concept called region proposal network. So it's a neural network that basically does the selective search job, or that does the region proposition job. So it proposes different regions. And the idea in here is so basic, so simple, that you would laugh at how simple it is. Very simply, you take the image, input image. Here's the input image. Pass it through the CNN once. So one application of the CNN. Just once. Now let me ask you, let's go before doing that. Can somebody remind me of the first algorithm we have seen for object detection? What does it do? It slides through the image with a
With a sliding window.
yeah. What is sliding over the image? So it's a classifier, right? So basically, it takes a classifier CNN and slides that CNN across the input image. That's what the initial algorithm that we discussed does. It's a very simple algorithm, very basic, very stupid algorithm, very slow, doesn't give good results, but that's what it does. Now we will be doing exactly the same thing, but instead of sliding the whole CNN on the image, we will do the inverse, the same thing as we did with fast RCNN. First, we take the image, pass it through the CNN, and in the convolutional feature map, you see the convolutional feature map, here it is. It's much smaller. So instead of being 600 by 1000, it is 60 by 40, much smaller image. So we will be sliding on this small convolutional feature map. And instead of sliding with a convolutional neural network classifier, we will only be sliding with a simple classifier. Usually it's just a basic, what is it called, fully connected neural network. But for the speed, for like the sake of improving the speed, we will see how it gets implemented to make it even faster than that. But as you can see, the idea of this region proposal network is very basic. It's exactly the same as we have discussed in the start of the lecture. So it takes the image, passes it through the CNN, and then slides a classifier here, step by step, over the convolutional feature map. And at this place, it just says, there is an object, there is no object. There is an object, there is no object. There is an object, there is no object. And that's it. That's all you do. So it's instead of searching like selective search, which was searching, for example, on the actual image, now we are sliding a classifier on the convolutional feature map. And that leads to hopefully much faster, of course, calculations, as we said. Yes. Very, very, very cool. Good question. Anwar. Oh, that's a great name. Wow. Anwar. Like it. So yeah, that's a great question from your friend Anwar. Basically what he said is, how can we slide a class the image. Okay, here's the image. Sorry, the internet connection is a bit bad right now. Can you still hear me, guys?
Yeah.
Nice. So instead of sliding, as we said, one single classifier through the convolutional feature map here, we will be sliding 9 classifiers. 9 fully connected neural networks will slide over the image. That is the answer. So some of them, as you can see in here, focus only on the yellow ones. Some of them are what is it called? Squares. One of them is a square, small square. So let's start with a small square, horizontal rectangle, vertical rectangle, and that gives you the small shapes. So it does take away 3 types of objects, 3 types of small objects. And then, as your friend has said, there are objects which are, different sizes. This, for the shapes, we did it, right? Shapes, it could be either square, horizontal rectangle, or vertical rectangle. We cannot do anything else because object detection only works with rectangles, right? It doesn't work with triangles or circles like that. You're not going to be able to do that, but you could still estimate each object as either a rectangle or a square, right? Now, the second part of your question was, they also have different sizes. Same thing. So whatever we just did for small, we will do it again for medium-sized objects. And we will do it again for big or large object. And that gives us 9 classifiers. Or in the terms that faster RCNN has used, we will be using 9 anchors. So these anchors are what's going to slide through the image or slide through the convolutional feature map and actually do the calculation. In this image, it might be a little bit confusing because you see the anchors are on the image in here and not being applied here. But this is just to show you basically what's happening, right? So these anchors that are being shown here are actually being applied on this here, on this location, right? In this way. They're being applied here. But just so that you understand what they are actually seeing when we apply on this part of the convolutional feature map, you are seeing it on the actual image in here. So just why exactly 9? Absolutely no reason. The first algorithm that they have proposed, they used 9, which is basically 3 times 3. Or as your friend has said, 3 sizes times 3 shapes. That was the intuition. Now there are newer architecture which don't use 9, they use 12, some others use 11, others use different techniques completely. Others actually allow you to train these anchor sizes. So these even anchor sizes and anchor shapes and the number of anchors are being trained in some architectures. So why exactly 9? For this faster RCNN architecture, they used 3 by 3, 3 sizes by 3 shapes, but it's not always going to be 9 for the future algorithms, right? As you can imagine, this is from, 2018, maybe something like that. So it's a little bit old, but it's still being used till now, right? But the newer versions, they allow you much more flexibility, much higher numbers or smaller numbers. If you are using a smaller architecture, you could use only 6 instead of 9, right? So it's up to you. But why exactly 9? It's just 3 by 3. Now let's go back and actually see the calculations here. So here, as I lied a little bit to you and said that we are applying 9 fully connected classifiers. This was the intuition, right? But how it gets implemented in real life, we are applying actually a CNN also on it. So it's again a convolutional filter or a couple of convolutional layers. Why are we doing that? Just to speed up calculations, because convolutional layers are much more parallelizable than actually fully connected layers. But here, since it's just one, it's kind of the same numbers or the same, multiplication and addition, but it's done much faster approach than just doing it through a fully connected layer. And how does it get done? Here, what we will have is a couple of 3 by 3 filters. And here we will have, what are they called? The number of channels is 512, mainly because the convolutional feature map is 512. And then we will split it into two types. Now let me first start with the lower part. The lower part is simple. Classification scores. Is it an object? Is it not an object? So this is not the actual classification where it says, this is a horse, this is a dog, this is a cat, this is a person. This is just classifying, is this an object or is it not an object? Simple binary classification in here. And this is why you have 9 by 2. So the 2 is binary classification, yes, no. 9, as we said, is for the number of channels, or the number, sorry, of anchors. 9 is the number of anchors. 60 and 40 are the actual sizes of the convolutional feature maps. Here we have 18 units. So we're actually applying this classifier through 18 convolutional neural network or convolutional kernels, which are doing the actual calculation, which is 9 times 2, right? So 9 anchors times yes, object, no, not object. So it becomes 18, 9 times 2. This is simple. Now let's go back to same question from Anwar. He said, there are different sizes and shapes. We simplified it and said that there are mainly 9 types of shapes, right? There is small, medium, large, and there are 3 types of what are they called? Shapes, which are rectangle, horizontal, square, square, horizontal, rectangle, and vertical rectangle. But there are, different aspect ratios, right? So maybe this is a horizontal square, or maybe a vertical square. I don't know. Yeah, this is a vertical square, and this is also a vertical square, right? So they have different sizes, even though they are both medium. They're not gigantic. Let me just do it again like this, right? So they are similar in size. They're both medium. They're both vertical rectangles, but they are not actually the same size. How can we solve this issue? Very simple. We have another set of, let's call them regressors. So this is a regression happening in here. And this regression, its job is to optimize the shape of the actual predicted object. So if the anchor shape was like this, but the object, let's say, was like this, so what's going to happen is, in this setup like this, in here, we are predicting, as you can see, 9 times 4. This 4 stands for the difference in the x coordinate, the difference in the y coordinate, the difference in the, what is it called? The difference in the height and the difference in the width. So it tries to predict the most optimal borders of your rectangle for that specific object. So this makes it much more customizable. It is a neural network that is being trained on the data itself. So it is fine-tuned to whatever data you're working with. So if it's medical data, if it's a zebra, if it's a white bear on the snow, whatever it is, this neural network is being trained specifically for that data set, meaning the performances are going to be great. And instead of just relying on specific heuristic or a greedy algorithm to give us, optimal object sizes and object borders, now we are using this neural network, the regression coefficients for boxes part, where it actually proposes the perfect and most optimal borders for whatever object you are training on. So this is basically it for the actual faster RCNN. It's a very simple algorithm, as you can see in here. Slide the window through the convolutional feature map using 9 anchor boxes. Here it is being referred to as K. So K is the hyperparameter. In faster RCNN, K is equal to 9. In other versions of the same architecture, they just have different improvements. Sometimes you will find it as 12, sometimes as 11, and sometimes as 6. So it's K is flexible as you wish. And here, what basically ends up happening is you will slide all of these anchors on the convolutional feature map. Each one of them is followed by two calculations. This is just, as we said, this is just a what is it called? Just a multi-layer perceptron, basically just a couple of multiplications and an addition. But it is being implemented through a CNN for improving, the parallelization of this calculation and making it much faster. One part goes to 2 times K, which is 2 times the number of anchors. And this gives you the scores, whether it's an object or not. So 2 stands for yes or no, binary classification layer. And then we have a regression layer 4 times the coordinates, or 4 times K, which is 4 times 9 in our case, 4 times 9 times 9 anchors. And the 4 stands for X, Y, width, and height. And this is basically the region proposal network, as you can see in here, right? So here, simply you have fast RCNN, which we have seen already. And here you have RPN, region proposal network, which is a simple neural network that is using a simple also algorithm, passes it through the CNN once, and then slides a couple of classifiers on the convolutional feature map. That gives you your region proposals, and then you give it to fast RCNN, and you finally have your object detector together in the same image. So this is it. This is the family of RCNN family. We have studied these 3 this week. Next lecture, so probably during this weekend, we will study the final architecture, which is mask RCNN, which is used for actually segmentation or for instance segmentation. But for now, what we have studied is RCNN, where it uses selective search, as you can see in here, region proposal, reason proposal. So both RCNN and fast RCNN, they use selective search. This one passes it 2,000 times through the CNN and has resizing happening on the image. This one only once goes through the image, only once goes through the CNN. So the whole image goes through the CNN only once. And then we use selective search with ROI pooling and just a simple division to find the regions inside the convolutional feature map. And then from there, we do the classification and bounding box regression. And then, of course, for faster RCNN, we completely removed the selective search operation and replaced it with region proposal network, which is much faster and much more tailored to your data set. And then it goes through the same architecture as fast RCNN. So this is it for the RCNN family. As we said, we will see how it gets improved to a mask RCNN, hopefully during the next lecture, where we speak about segmentation and specifically about instance segmentation. Does anybody have a question about the family of RCNN for object detection first? All good? So, хорошо. Let's go to YOLO now. So what we have seen so far is the following. We've spoken about object detection in general, applications, and what are they called, application areas and what it is. We spoke about intersection over union. We spoke about non-maximum suppression, and we spoke about selective search. We spoke about RCNN, fast RCNN, and faster RCNN. And faster RCNN is an extremely fast algorithm, so you could use it actually right now with very good performances and very good speed. And then we have the last one, which is Detectron which is YOLO. And for YOLO, what we're going to do is we'll check the architecture. We will speak about it in detail, but you will see that the similarities between the two make the learning for YOLO much faster and the understanding of YOLO much easier. Before we go into YOLO, we will speak about the library Detectron. We will be seeing it a lot during today's lab. Detectron is basically a library that is made by Facebook, and their job was to implement as many computer vision models as possible. They train them at their own labs, and they give you some pre-trained weights which are very well well tuned and well trained. And of course, it is written fully in PyTorch, meaning you have access to extremely lower details. You can get the gradients at any specific layer inside the algorithm. You can get the output of any specific layer of your model. You can get anything you want to it. You can get the weights, you can get the biases, you can get anything you want from that model in a very simple way. And we will see that during the lab. How can we access the model architecture? How can we change the model architecture very easily and very quickly? And it provides trained models for a variety of tasks, such as, of course, object detection, as we were looking here, object segmentation or instance segmentation is most likely known, dense pose estimation, panoptic segmentation, landmark detection, and much more. Now let's go to YOLO. So this is the architecture for YOLO. As you can see, it's a little bit different. First of all, has the color purple. We didn't have that before. But other than that, it's exactly the same. And before we go into the whole architecture, I would like you to ignore everything outside of this yellow box. Only focus your attention on the yellow box. So inside this yellow box, let me try to zoom in. Maybe I can do that. I cannot. So inside this yellow box, what do we have? A couple of residual blocks. Ignore that word and call that convolutional layers. So we have a couple of convolutional layers, followed by what is being called in here as a detection layer. Ignore that word and consider that also as a convolutional layer. So these two are both convolutional layers. We have a couple of additions and concatenations. Also ignore that. We will speak about it a little bit later on. And for further layers, it just means duplications, right? So just more convolutional layers, just a lot larger. Upsampling, also ignore it. We will not speak about it for now until we go outside of the yellow box. But for now, what you are seeing is very simple. We have seen this before. Image goes through a couple of convolutional layers, gives you a convolutional feature map. So this here is just a smaller version of the image, but it's not actually the image. It's just a convolutional feature map. Convolutional feature map. Can somebody tell me how can you do the classification on a convolutional feature map from the RPN? Remind me of RPN. What does it do? Once you have the actual CNN convolutional feature map, how can you do the classification and do the object detection? Hello. It has the words, yes, region, proposal, regions, RPNs. But how does it do that? What is the mechanism? It starts with N, C, A and C. Sliding window with classifiers, exactly. But what is it called? It's the sliding anchors, yes. So it just slides a couple of anchors through the actual convolutional feature maps. That's exactly what's going to happen. Let's leave that place and come back here. So this is what happens in the YOLO. We take the image, pass it through a couple of CNN layers of convolutional layers, gives you a convolutional feature map, and then you apply these anchors here at each individual pixel. And these anchors, in this case, we have 3 boxes. We have only 3 sizes or 3 shapes. Sorry, we only have 3 shapes here. Previously, we had 9, right? Now we only have 3, but we will see why. So this is B, which is times 3. The content here is the same. So we have the bounding box coordinates, which is 4. Remember, 4 times 9. In this case, 4 times 3. Objectness score, which is whether it's an object or not. And an extra one in here, which is the classification score. So the main difference between faster RCNN and YOLO is exactly in the name. YOLO stands for you look only once. So you look at the image only once and perform the classification immediately. Whereas for faster RCNN, it looks at the image, proposes the regions, and then tries to classify these regions. Unlike with YOLO, immediately as it looks through with anchors, it doesn't just do coordinates and objectness score, but also does classification scores. And here, as you can imagine, times 3 stands for rectangle or square, horizontal rectangle, and vertical rectangle. So this is the times 3 where it is happening. So very simple operation, very similar to what we have seen already. Now, if we come back here, what do we have? We have the following. We have this, we have understood at least this first initial rectangle. Now let's go out of this and let's look now at the big picture. You see this first big rectangle? We said it has 3 anchors. In this level, we have 3 anchors. How many levels like this do we have? We have 3. 1, 2, and here's the third. And each one of them has 3. So in total, we actually also have 9 anchors for YOLO. But they get applied on different scales of the image. So what ends up, we take the image, shrink it through, of course, convolutional layers. As you know, convolutional layers, they reduce the size of the image. So we shrink the input image 32 times. So the stride in here is 32 times at the first level. At this first level, if I tell you we have a big dog in the image, a very big dog, occupies the whole thing, can you still see the big dog even if you resize the image 32 times? If you shrink the image 32 times, can you still see the dog a little bit? Yes or no? Хорошо, yes. If I said that there is a very small object, like teeny tiny object on the background, and you shrink that image 32 times, can you actually see that small object after shrinking it 32 times? Нет. So the first scale, this first scale only works for large objects. Now you can guess, when we go to stride of 16, if we have a medium-sized object in the image, we shrink it 16 times, we can still find traces of the medium object. So scale 2 is for medium objects. And then we have scale 3, which is only stride of 8. So even if it was a small object, shrinking it only by 8 times will allow us to find potential locations of that same object, small object. So basically, this is the small scale search or small size search. The first scale searches for large objects, second scale searches for medium objects, and final scale searches for smaller objects. And as you can see in here, since we make this image, we make it super small, so it's 32 times smaller, we must make it big again to make it around 16. So we must make the size bigger. How do we do that? With upsampling layers. Upsampling layers are very basic, a very simple concept. So if you have pixel with content 2, you will make it or replace it with 4. 2. So we make it much bigger, right? It's just a simple resizing operation, making it bigger. It's a very simple layer. No need to go into detail about it. So here we make it smaller, and then we make it bigger, and then we make it bigger again, right? So as you can see, it's not very intuitive. Why not start from, the big image, search for small objects here, and then make it smaller with convolutional layers slowly, and make it smaller completely and search for the, instead of, making it small and then up such calculations. The only reason here is searching for large objects first allow you to understand the image. So you now have a deeper understanding of what's the global vision of the image. What are the big objects inside the image? When you have that information and you go to searching for smaller images, smaller objects, you're much more likely to do better job at classifying them or at detecting them than just doing it directly through the detection of small and then medium and then large. So this is the YOLO architecture. It's a very simple architecture, as we said, very basic and straightforward. Any questions about the YOLO for now? This is YOLO v3. And we will, during the lab, we will see different versions of YOLO, as we said, YOLO v4, YOLO v5, YOLO v6, YOLO PP, YOLO v7, and YOLO v8. Different versions of YOLO. Some of them are good, some of them are bad. YOLO R, for example, is quite nice too. YOLO X, I think, also is nice. So there are so many versions of YOLO, and we will see during the lab how to use all of them in 5 minutes. So I want you guys to have the ability to train or to get started training your object detector in less than 5 minutes tops. In 5 minutes, you should already be doing the calculations and no code is required. So it's very, basically we extract more features with upsampling like in the unit. Exactly. So if you know the unit, we will speak about unit and the segmentation class. But yes, exactly like the unit for the same reason of basically the using the unit. Yes, absolutely. So that's it for the actual course part or the actual lecture part of this course. So now do you want to take a 5 minutes break and go to the lab, or do you want to go through the lab really quickly because the actual lab is like, I don't know, 20-30 minutes maximum. And then of course I will release you guys so then you go back and work on your projects. Let's go to the lab now. Okay, so let's go to the lab now and finish much faster than, let's have the lab. Okay, so we have a consensus. Let's continue then with the lab and get started. So for the lab part, I haven't prepared anything. I will do it right now with you from scratch. So let's do the lab together. First, I will write the name Detectron 2 and search on Google. Very simple search, you see? Detectron 2 sends the first link, gives you a GitHub repo. You go to the GitHub repo, amazing GitHub repo with lots of documentation and stuff. I don't care. I search for the word called Colab. You see this? Colab notebook. I press, opens a new window. Colab notebook is started. And we're good. And that is literally all that I will be doing. That's it. You have the lab. This is the lab. So as you can see, it's a bit slow, mainly because my internet is quite horrible. But usually it loads pretty fast. Here it is. So this gives you a tutorial on how to use Detectron with already a dataset example in hand, with lots of examples on how to work with videos, how to work on multiple images, how to fine tune, and how to even monitor the performances of this model. Very quickly, I will do runtime run all. Copy to drive first, huh? First operation, copy to drive. Sorry. Okay, it's running. So it's installing. This is pretty, sorry. It's creating the actual copy is right. I don't care. So here it is, it's running. This one is just checking that you have good Torch installation, you have good CUDA versions, you have good Detectron versions, everything is nice. A couple of imports, completely useless for now. What we're going to do is wget, which is just downloading a certain image from a repo for a what is it called here? I think this is Coco dataset, the validation dataset from 2017. You look at it, and here it is. This is the image, a horse, a person, a couple of people in the background, some umbrellas, and that's it. And here we go. We are showing this image here too. Amazing image, very nice. Now we will start by actually using an algorithm. First, what do? Is we get config. So this get config function allows you to tune or basically configure the actual environment of your what is it called? Of your model or of your architecture. And I don't know why I cannot. Here I can. I cannot get it. Okay, said CFG. So it's training, huh? Yeah, it's training. It's gonna take some time for me to actually run this code. Let me open it in another window, and just to show you guys, because it takes some time to train. So I will run another window, and basically in this window we will execute the code. But if you want to understand what that config thing was doing, go here. Sorry, maybe here. Configs. My internet is pretty slow, but let's see. We were working with what is it called? Here it is. We go back, here it is. So config Coco instance segmentation Mascar CNN. So here we're using Mascar CNN. Nice. Coco instance segmentation, or let's go Coco detection instead.
Жестко.
Свидание, ладно.
Мгм.
Sorry guys, my internet, as I said, it's quite trash. Hopefully it's back now. Let's see. Nope. Close this one. Close this one. Right. I hope it's, yeah, this one is continuing to train, so that's nice. Let's continue the lecture. Yep. Oh, this one is still also calculating. Or is it downloading? It's installing. Okay, let's wait for it. But the actual, yeah, as we said in here, thing goes here. Go back. So yeah, here you're able to basically do or look at the configs and see what you can change in these configs. So here, for example, we're using this base RCNN FPN, and we can just go back to it and see what it is. Configs. base RCN and FPN, right? This one. And as you can see in here, you can change anything you want. You could change the architecture, you can change the name, you can change these output feature names, input feature names, the anchors. So these are the anchors. You can change the aspect ratios as you wish, right? This is 0.5, 1, and 2.0. So this means small and large and medium. These are the names of the features. You could change everything you want to change in here. ROI heads, region of interest heads, region of interest box heads, which is basically just the fast RCNN. Here you have ROI, where's it called? Yeah, ROI mask head. This is the classifier. The data set that you want to use. So if you want to set up a training data set, here it is. You want to set up a testing data set, here it is. And later on, we will see how to register a new data set. If you want to bring in your own data set, how can you register that data set? Here you can change, for example, how many images per batch you want to load to your model. What is the base learning rate? This one are the steps. How max iterations basically means how many iterations you will train for. So here we will be training for 90,000 iterations. It's a lot, as you can imagine. And during this 90,000 training iterations, it takes a lot of time, right? It takes, I don't know, like a day or so to train all of that. So we would like to basically save a couple of weights at different steps. And this is what the steps symbolizes. It just means times when your model will be saving the weights during the training, just so that you have something that's, so if you stop, you don't lose your work completely and you have something at least. So this is what the get config allows you to do here. Let's go back. So get config allows you to get those configs, but in a much simpler way. So in a Pythonic way, you can actually tune or change them, right? So here, configs merge from file and you get the configurations for this one. Coco instance segmentation, mask RCNN, R50, FPN, 3x, YAML file. As you have seen, all of these files, they exist in here. If you want to change the architecture, just come here and find whatever architecture you would like to use, change that, and that's all you need to do. The weights, also the weights are located in the same place. All you have to do is give it the name of the model, and the model zoo will basically load for you the weights, the model zoo for, yeah, model zoo, sorry. I Detectron 2. And here you can see all of these model weights. Here you go. You can choose based on inference time, training time. This is the average precision, which is the way that we calculate the performances of the model. And here you can download the metrics, you can download the model itself, and you can get basically the link to the model's weights. Based on the size, you can do whatever you want. Up to you. As you can see, it's a lot of models, huh? All of these, you can choose whatever you want. Put the correct config file and the correct checkpoint URL or the correct weights. So these are the weights. And you're good to go. Here, what you will be creating is a default predictor. Default predictor is a simple wrapper class that allows you to perform the detection, object detection, the prediction of object detection very quickly and very simply, allows you to get some beautiful designs, beautiful visualizations, beautiful metrics. All of that allows you to do it really quickly in a way that is very similar to just training using PyTorch, right? As if you are training a simple image classifier and not a very complicated architecture, something like faster RCNN, right? We've seen faster RCNN. It's not just like a simple CNN with a few applications and just direct application. No, this one is a much more complex, much more deeper algorithm that is much harder to tune. But here, using this default predictor, you can call the predictor here as if it was a PyTorch model and just send the image, immediately gives you the outputs. So here, if we look at the outputs gives you this predicted classes. So here we have class 17, multiple versions of class 0, and 25, 25, and class 24. Also gives you the actual coordinates, right? This is the classes. These are the coordinates, X, Y, width, and height. And here we can visualize the results of applying our model on that single image. And here it gives you person 100%, a horse 100%, umbrella, person, as you can see in here. And all of this visualization is done through some basic Python code. As you can see here, first it takes it to the CPU, because if you look closely, the device, it is being located in the CUDA device. So you have to bring it back to the CPU and then perform your visualizations as follows. Pretty simply, you have a backpack in here, person. The results are quite nice. The results are actually very good. Even the head of this person was predicted as a person. So it's pretty good results overall. Now we have seen how to use it. Let's actually see how to train it, right? Now the question becomes a bit more complicated. How can you train such a model? Not how can you use such a model? And instead of using a default predictor, you're gonna use a default trainer, and that's it. Very simple technique. But before that, you need the training data set. So here we are downloading a training data set from their, I think, repo. This is a Matterport, I don't know, some person. And he was the first person to actually create the Mascar CNN. So they're using this balloon data set, a very tiny data set, small data set, to actually train it. They download the data set. Let's look at the downloaded data. Here it is. Training data, images. Here they are. Validation data, also a couple of images, and a JSON file. If you look at the JSON file, it will just be image name. Wow, what happened? Okay, sorry. Yes, so it will be image name followed by a couple of, the size of the image, file name, and then the actual bounding boxes and the classes for each one of these things. Here, we're not going to be speaking about bounding boxes. We're speaking about segmentation for this case. We're not doing actual class object detection. We're actually doing segmentation, but we will see how to do the conversion between segmentation and object detection. So as we said, you have a JSON file, contains the width and height of that, or you can get it from the actual file name or from the actual image. You give it a random index, or just like a specific index that is specific to that image only, so that the model can later on have a value that is unique for each image. You give it the height and width for each record, and then you go through the objects. For each annotation or for each object, you take this all points X, so it gives you the X coordinate for all the points, Y coordinates for all the points. We will explain this part during the segmentation lecture or segmentation lab. But for now, as you can see, it creates this bounding box using the smallest X point, the smallest Y point, the biggest X point, and the biggest Y point. So if you look at it, here's the image. This is your object. This represents the smallest X and smallest Y. So these are the smallest X and smallest Y. This is the largest X and largest Y. Sorry, like this and like this. And here is your object. It is trapped within these 2 points. Within these 2 points, you found your object. And this is a way to basically give the actual annotations to the model. As we said, you can do things like XY, XY. You can do things like XY and what is it called? Width and height. You can do different things, up to you. So here, this box mode, if you go to it, box mode Detectron, and you will find multiple versions of it. One is called XY, XY. Another one is called XY width and height, as you can see it here. Another one is called XY, XY relative position to the image. So it's between 0 and 1. These ones are the absolute coordinates. These are also absolute coordinates. You also have the ability to do XY width and height relative to the size of the image. So divided by the size of the image. And the last one is XY WHA absolute. What does the A stand for? So XY is the center of the rotated one, and A is the angle of the rotation. So if your object is something like this, you can still represent that, but this is a lot more complicated than a simple what we are describing here in our algorithms, which is just the faster RCNN, which does not take the angle in here. So this one, we're not going to be using it, but any of these, you can change between them however you want. It's up to you. Very easy change. Just come here, change it. And instead of using the smallest X and smallest Y, largest X and largest Y, you can just use the smallest X and smallest Y with the, what is it called? The center, or you could use the width and height. Everything you want, you can do it. So it's just a different calculation from these 4 values. Very easy way. And here, since we only have one category or one class, which is balloon, in this example, it's going to be pretty simple. So we just put index is equal to 0. The category ID is equal to 0 for all objects. If later on, especially for your homework, you will have multiple objects, if that is the case, what you're going to be doing is you will create multiple IDs for multiple classes. And how do you put these IDs? Through this thing classes. So for example, if you have thing classes, this is balloon. The first one is balloon. If the next one is person, so the ID of person becomes 1. Of class person becomes 1. If you have here a car, the ID of category car becomes 2, right? So it's very simple. This is where you get the ID from. And that's it. Here you will register your data set. This is called registering the data set in the dataset catalog. Remember here, we had 2 training data sets, or we had 2 data sets. This is the training data set. This is the validation data set. These data sets are registered by default in the dataset catalog that comes with Detectron. And if you bring your own new data set, you must register that new data set too. Very simply like this, you call the register data set from the catalog 1, and then you add your classes to it in this matter. And that's it. Now you have your data set registered. Here we are sampling 3 images from that data set just so that we see it. So it takes the balloon, everything is good. And here we're doing the training. Now remember, training very simple, like we did the predictions. Default trainer, get config, you give it the actual, what is it called, configs, you give it the actual weights that it should start from, and from here you are good to go. From here you are absolutely good to go, and you can simply start doing your training by simply providing what is the training, what is the training data set, what is the testing data set. In this case, we don't have it, we did not specify it, but you can specify it if you wanted. Number of workers for the data loader. So this allows you to increase or decrease the number of workers. This depends on how many CPU, how much your CPU is good and how much your what is it called, RAM is good. Here, this is the images per batch. In this case, 2 is pretty small, but if you have a very large, GPU, you can go crazy and pick something bigger. This is the learning rate. You can choose something smaller, something bigger. It's up to you. So, this is fine-tuning step. Maximum iterations is pretty small, as you can see in here, just 300. So we can do it fast for this lab. But if you are building for a big, complicated data set, a good rule of thumb is iterations is equal to 2000 times the number of classes. So if you are building a data set with, I don't know, 10 classes, your maximum iterations should be around 20,000, right? Very simple rule of thumb, 2000 times the number of classes. Very simple one. Here, number of classes is equal to 1. This is the batch size for the ROI heads, which is the fast RCNN architecture. It also has a batch size, as you can imagine, since it's a 2-step approach for the neural network. The larger it is, the faster, but you must remember that it will consume more RAM. Other than that, here's the architecture. So as we said, this is something that is based on Python or PyTorch. So you can access each one of these layers, convolutional layers. Again, we're seeing them again. Here again, everything's good. And a couple of convolutional layers until we reach the RPN in here. So this is the RPN. And here you have the standard RPN head with a couple of convolutional layers. let's see the anchor deltas. As you can see, these are the anchors. Anchor generator. Here's the call for anchors. And the actual ROI head. This is the output size 7x7. Not this is not what I want. Let me check here. 126x3. So it's 3x3 in here, the kernel size. Yeah, what I want to see is the number of anchors. We don't have that here, but it's okay. Level poolers, we don't care about that. The flattening, this is a pretty easy step. Box predictors, this is it. 1024, and then it gives you 2 for each category. So this is the actual, yeah, this is the ROI head, right? Yeah, this is it. Yeah, so here it gives you 2 for whether it's an object or not, and 4 for the actual coordinates, XY, XY, or XY, WH for width and height. And then we go down, this is the ROI pooling, and then we have the mask RCN and head. We do not care about this one. Let's check for something should have a head of 1. This is the predictor. Yes, here's the predictor. This is the predictor. It just basically tells you what is the actual class, which basically gives you the classification. Here it's telling you what is your data set, like what is it contain, what contains your data set. Here we have 225 balloons. It tells you there are 61 images. All of them are 1 categories. This is just telling you some information about the training. You could take a look at it. This is telling you that it's not using these default values because these are category specific. These are the shapes of the places where you are actually doing the classification. So here the classification score has 81 times 1024, but for us it's going to be 2 times 1024 because we have just 1 category and it's being done as 1 versus nothing or background. Here we are training 81, which is 80 plus 1 or 80 classes versus 1 background. Here again, the same issue, 80 versus 81 versus 2. This is also the same issue, 320 times 8 divided by 80 gives you basically 4. And this one is we have only 1 class. This one we have 80 classes. Same thing. So these are just basically telling you that we are not using the pre-trained weights or pre-trained weights for these specific layers because they are class specific. As we have seen previously in fine-tuning, you must manually remove those features and replace them with the features that you are actually building. But in our case, this is being done by default by Detectron, which simplifies the work a lot for us. As you can see, I did not do any coding so far. I did not manually do any of the code. All of it was being done by Detectron. So here we see that the training is happening. The loss functions are going down, classification loss, total loss, regression loss, and then of course the mask loss. We're not going to look into that because it's part of the segmentation lecture. We will speak about it on the next one. Here it tells you some deltas and the learning rates, how they are being changed. Pretty easy overall. Here you can see the dashboard. Let's check, for example, the actual loss. This is the learning rate, how it is being trained. You see how it's increasing very slowly. Here's the loss. Okay, it's a bad loss. Let's go for the classification loss. Here, the classification loss is going down. Very good. Good for us. This is nice. And now we have a trained model. So if I go here, close this. Somewhere should be a classification model. So it should be a trained model. Let me see. We said we are going to save it. Where? Output directory. Where is this output directory? It's for see config output directory. Did we? No, did not. No. Where did we define it? Okay, where is this output directory? I think it's output. Yeah, here it is. So here's the output directory. And this gives you the model final. In here, as you can see, this is the final model that we have, the trained model. This gives you the JSON for the metrics. So if you want to do some, why did it disappear? If you want to do some, I don't know, hyperparameter tuning that you want to build, you always have this JSON that you could use and work from. Last checkpoint, this is the instances predictions, different, weights, different results here. So this is the results for the testing. What is this? validation results, also pretty good. So it gives you access to everything. Let's go down. This is a couple of examples of applying it. So applying it again through the default predictor. Now we have the model. You see, this is the model, final model. The weights, we give them through the final model like this. This is the what is it called? The score for the inference time. So this is the threshold for the inference time. Anything that is predicted with a confidence score less than 0.7 will not be showing in this image. Here we see the balloon was predicted with 100%. This one was misclassified as a balloon. So you know during the monitoring setup, you could try to bring in the concept of chair so that the model, when it is training, it recognizes the difference between a chair and a balloon. But since you are only training with a balloon, now everything is a balloon. Anything that is anything that is circular is a balloon. So that makes it very hard for the model to actually understand the difference. But if you give it some samples with chairs, you're good to go. Here we're going for the evaluation part, but for the evaluation part, we will have an actual lecture first before we go into that. So hopefully next weekend, we will speak a little bit more about the evaluation of an object detection model. How does it work? How do we go from something so simple as precision and recall and F1 scores into something that works for something complicated like object detection? And also for segmentation, it works very well too. So that's it mainly for today's lab. So the lab is pretty short, as I said. It's going to be very quick, only about faster RCNN for now. Next week, we will also speak about, as we said, what is it called? Help me out. We will speak about validation or how to evaluate the model. And then we will speak about YOLO and the different versions of YOLO v4, YOLO v5, YOLO v6. And as I said during last week, we will be using something called RoboFlow. So the labs for object detection and for segmentation require zero coding. But we will do a lot of manual labor when we create our own data set. So this is the first homework that I will be giving you guys. Using your own phone, go around the city of Innopolis and take around, I don't know, 100 pictures of the same class. So for example, some students, they go to Petorchka and they take pictures of avocados. They buy a couple of avocados and they take pictures of avocados around Innopolis. Take 100 pictures around Innopolis of avocados and create your own data set, a data set that you have manually annotated. Some of them are in the dark, some of them are in the night, some of them are in the morning, some of them with a good background, some of them with a clear background, some of them with a very mushy background. Up to you. Create 100 images manually from your own, environment. Of course, do not take pictures of people or pictures of, I don't know, some, military bases. Just take something that is very simple to use. I don't know, a chair. Take pictures of your own chair in your room with different positions. Take pictures of, I don't know, animes that you like. Anything you want, you can make it as a picture, okay? All good. So for your next lab, I expect everybody will come with 100 pictures. And you guys will upload these 100 pictures onto RoboFlow and annotate them manually. So we will see how to do that together, but it will be pretty easy to do. It should not take you more than 2 seconds per picture. So in total, it will be like 100 seconds, 100 times, let's say 5. So 500 seconds, around like 10 minutes. So it will be like a 10-minute job for you to annotate that whole data set really quickly. Okay? Next lab is tomorrow, isn't it? It is tomorrow? Really? We have a lecture tomorrow? I didn't know. Nobody told me. Where did you hear this information that the next lab is tomorrow? Don't we have like a lecture on Monday and one on Sundays or Saturdays? I think
Saturday.
Saturday, yeah. So one on, yeah, whatever it is. One on the weekend and one on Monday. So it's not tomorrow.
This is from the old version of the timetable, I think.
Oh, Oh, okay, that's bad. Tablocha.
Yeah, I'm checking the current schedule and there's nothing tomorrow.
Okay, perfect. So see you guys on the weekend, and be prepared to have 100 images of a certain object or a couple of objects. You might want to put like a banana versus an avocado, and that's, you know, that makes it a bit harder, which is more challenging, which is a bit better. But it's up to you. As long as you have 100 images of a certain object that you take from your real life, it's all good for me. So thanks a lot, everybody, and see you on the weekend.
Goodbye.
Bye bye.
See you.
Bye-bye.